All right, so now for example number 2, I apologize for that. For example number 2, we have to do something different. What we want to do is we want to figure out, we have the function f of x is equal to the square root of x squared plus 1. And they give us the parameter x goes from -1 to 1. Okay. And in this particular case, we're talking about the mean value theorem, which if you guys probably haven't memorized it yet, but it's not hard to memorize. It's f prime of c is equal to f of b minus f of a, okay, all over b minus a. So now in this scenario, we have f prime of c should be equal to f of b. So remember, this is a comma b. I'm going to write it down a little different on this example. F of 1 minus f of -1 all over 1 minus minus 1. Does that make sense? Oh, I got ahead of myself. This should be a. Okay? I'll put that in parentheses so it doesn't confuse you guys. So now what this means is I should be able to take the derivative of f of x, and this should work. Now, what the textbook says is that it fails. In other words, it doesn't satisfy this condition. So we got to go back to the formal definition. Remember that the formal definition said if f is continuous from a to b and differentiable. So there's the two parts. Now, if this doesn't satisfy this condition, what does that tell you?
Can't do it.
Can't do it. Why?
Because it doesn't complete the theorem.
Yeah, either it's not differentiable or it's not continuous. Does that make sense?
Yep.
So now what would cause it to be discontinuous?
Because
A domain restriction. Do we have a square root up there?
yes.
Yeah. What are the domain restrictions on square roots? Can't take a negative square root, right? But now you notice that x is squared.
Oh.
So what's -1 squared?
1.
1. Can we take the square root of 1?
Yes.
Yeah. So that what's the domain of f of x?
All real numbers.
All real numbers. So it is continuous, so it must not be differentiable. Now, I already know the answer. 1, because I have the textbook, but 2, I'm going to graph this thing. Let's see what it looks like. So if I graph the function, and I say the square root of x squared plus 1, right? When you take the square root of a square, there's an interesting thing that takes place. Let's look at the graph of this, okay? What do you notice about the graph?
Absolute value. Oh.
Yeah, it looks just like an absolute value, but
It's a corner.
it's a corner. And what do we remember about corners?
Can't do the thing.
Not, she said not differentiable. Okay, so it's not differentiable. That's why it doesn't satisfy. All right, but let's go through the motions and we'll see why it doesn't satisfy. All right. So now if we were to crank through this, if I were to evaluate f of 1, I would say the square root of 1 squared plus 1. This is 1 squared, which is 1, right? And then the square root of that is 1 plus 1 is just 2. So on my graph, I've got 1 comma 2. Now if I say f of -1, it's the same thing, I think, right? Except we've got -1 squared plus 1. When we square the -1, or is that the base? How does that work?
What? Wouldn't that be 2?
What would that be?
Well, because or would it be 0?
Yeah, this is a special case. But actually it ends up becoming 2, right? So if I do the exponent and then I take the square root of it, it turns out to be a positive 1, right? Okay.
If you want it to be.
If you want it to be. because I can't take out the negative. There's actually, remember that whenever we do a plus or minus, or whenever we take the square root of something, we tack on the plus or minus. But in this scenario, most of the time we only consider the principal root. Does that make sense?
Yes.
Okay. All right, so we get 2 and 2. Now, if I wanted to verify those results, if I go to my graph and I hit trace, and I enter in -1, yeah, y equals 2, right? And if I enter in 1, whoops, gotta hit the button. When x equals 1, y equals 2. So that squaring thing is like an absolute value effect when you think about it, right? In fact, we will use that technique later on. All right? Because what we're doing when we square it and then we take the square root, no matter what, the answer is positive, right? Does that make sense? No matter what value for x is. Wasn't that the same as an absolute value?
Yeah.
Yeah? Okay. So now what does that mean for this theorem? That means that f prime of c should equal, what do we have in the top? 2 minus 2 all over 1 plus 1. Well, it's just 0 over 2, which is just 0, right? So there should be, at some point on this curve, f prime should equal 0. So now if we just continue with this mean value theorem, not thinking it through, then we might say to ourselves, okay, we have the function f of x is equal to the square root of x squared plus 1. And f prime of x then would be, okay, so this is where it gets tricky. We have x squared raised to the 1/2 plus 1, right? Is that right?
I think so.
Now, there's lots of ways that you could approach this. I could, that's not f prime, that's just another way to write f. Right? I haven't even begun to do the differentiation. That's just another way to write f. Okay? Well, I could leave it the way it is and use the power rule and plug it in and then use the chain rule. But I could also algebraically, like, what do I do with those two numbers?
You multiply it.
Yeah, normally algebraically what I do is I just multiply it, which would be x to the first power plus 1.
Oh.
Right? If we were just doing algebra. But we have to be careful with that, right? Some of you might try to do it that way. And if you were to do that, you would have f prime of x is just equal to 1. But we know what the original graph is. So that's not true for all x. So now the reason I wrote this down is I wanted to show you, hey, look, this is one way to get the answer. But now we're at a level of mathematics where we can't just crank through things. We've got to crank through, double check the graph, think about it, think about it, think about it, think about it.
Wait,
That's one way to do it. What if I were to do this, though? What if I were to actually take the derivative of this? In other words, if I left it alone and I had x squared raised to the 1/2 plus 1. That's one way to do it. So I would get f prime of x would be equal to, toss the 1/2 to the front, right? Then I would have the stuff on the inside, which is x squared, times the derivative. Wait, it's the x squared raised to the -3/2, right? Then you tack on the derivative. That's one way to do it, right? Yes. Yes, quickly. Now, is this valid or invalid?
Invalid.
No, it's valid. Yeah, you have your hand up.
Yes, why, for like back to the thing on the left, why is that time 1? What is, don't you like plug in the x or something?
Mm-hmm.
Why is it just 1? Like, what did you plug in for x?
We didn't plug anything in for x. What's your question here? Why did we just leave it like this?
I mean, like, why is it just 1 instead of the x plus 1?
What's the derivative of x?
1.
1.
So, I
Does that make sense?
Oh,
Any other questions?
sorry. I didn't realize.
Wait, can you go back up to the first part of the?
This here?
Yeah, just good. Okay.
Okay.
Sorry, I was not even realizing that there was a derivative. I'm so sorry about it.
Now, Mr. Adams is not intentionally attempting to confuse you, but I do want to, although you may feel that way, I do want you to understand that not everything is worked out nice and neat. Up until this point, the textbooks and your homework and your math teachers have given you problems that are easy and it's simple and it's the same way every time. This particular problem you have to think, okay? So what we got is we have our original function here, and f of x is equal to the square root of x squared plus 1, and we could do all kinds of stuff. We could do the stuff in red and differentiate. If we leave it the way it is and differentiate, we'll get that answer, and both of them are true. However, this is only true for x greater than 0. Okay? I think that I'd have to double check my math, but I think this would be true for all values of x. But really, another way, a simpler way to do it, would be to think of it like this. If I say f of x is equal to the square root of x squared plus 1, we could think that that is the same as the absolute value of x plus 1. Does that make sense? We could think that. Or another way that we could think of it is we could think of it as plus or minus the square root of x squared, which would be plus or minus x plus 1. Right? Because technically when we take the square root of something, there's the potential of it being a positive or a negative solution. Now, if we take this route, which, by the way, this is the same as this, if we take this route, then we have two f's of x, right? So we would have f of x is equal to a positive x plus 1, which is what we got the first time, or f of x is equal to negative x plus 1. Now that would work, those two, and that would have to be like a piecewise function. Right, and so here is here's an interesting thing. This works out better, and then you'd have to differentiate both of them. So what I'm going to do, just to show you guys what we're doing here. Now, if I were to graph those two functions, in other words, if I were to come in here and I were to say, you can see. By the way, as I do this, you guys really should be doing this on your calculator as well. So what I should have done is I should have put the plus sign here, right? And then put in negative x plus 1, and then put the restriction of x is less than, second math, 5 less than 0. Okay, so now that's what that one. Now, the shortcut way, so this is how the second graph is the same function, it's just a piecewise version of it. And truthfully, I could set one of them to be equal to 0. It doesn't matter which one. I could arbitrarily choose one or the other. It doesn't matter. And so, when I do that, that's one way to graph it. Now, another way to graph it is if I come in here and I do the absolute value of x plus 1. Okay? Now, watch what happens when I graph this. The red line is the original function. Okay? Now, we're going to get like a green line, which is my piecewise function. Hey, exact same thing. Not defined at 0 because I kind of skipped that. The purple one is an absolute value function. So the reason I'm taking so much time on this one example is that I want you to know is that when we run across an absolute value function, sometimes we could rewrite it as a piecewise function, and then we would differentiate the left-hand side and the right-hand side. But we all see clearly when x equals 0 that it's not differentiable. And that would be the point in which our slope would equal what we got here. So, before we get lost in all this, what was our original task? Well, our original task was to determine when f prime of c equaled 0. Now what that looks like is basically we have a function, right, that looks like this. It comes down and it goes up. And when we evaluate it from -1 to 1, our secant line, we have some corresponding values here, but our secant line has a slope of 0. And we want to find when f prime has that. Well, really, technically, f prime has that when, but technically it doesn't exist there, right? Because f prime can't exist at x equals 0 because it's a corner, right? Does that make sense? I kind of overtaught this example, but I hope it'll help you later on down the road. Because the reason I say that is when you take the AP exam, they'll give you one of these functions that has a corner or a cusp. And they'll rig it in a way where you can't take, and people will sit there for 45 minutes trying to figure out how to solve the problem. But you know that you can just simply say f prime of 0 does not exist, and move on to the next question. But they might ask you, what is the slope as you approach from -infinity? Well, you can say it's a -1. They might ask you what the slope is as you approach from positive infinity. You can say +1. Does that make sense? Well, what is the slope at x equals 0? Doesn't exist. It's a corner. That's where that comes from. Okay, any questions about this before we move forward? So what did I just say? What's the answer?
It can't exist.
Can't exist. It can't exist. And so remember, there were two conditions, right? We said if f is continuous, f is differentiable. So this is our A and this is our B. The problem is when x equals 0, it's not differentiable. And that's the exact point where they would equal, if we could do it mathematically. Does that make sense?
Yeah.
All right, so let's move on to the next one.